Welcome to Jack's Problem Solving channel. Today we'll be going over the reverse integer problem. It's a programming problem where the input is any given integer, positive or negative, and the output should be the reverse of this integer, or with all the digits reversed in order. It sounds like it's an easy thing for humans to do, but for a computer to do it, we have to be careful how exactly we implement this code. So let's get into the details. So the problem statement, just to reiterate, is given an integer, return the reverse. Whenever given a problem, I always like to draw a figure to represent the problem. So in this case, the figure is fairly straightforward, but in the future, we'll be solving more complex problems with multiple inputs, and there could be multiple dependencies. But in this particular problem, the input is just an integer input, x, and the output is another integer, but we're reversed. The caveat is that when the overflow occurs, the specification for this function is that we should return 0 in this case. So this diagram captures the essence of this problem. Now let's dive into the details of how reverse is implemented. Before we implement the reverse function, we should have an idea in our mind how it will be implemented. So to do that, I usually like to draw an example. So in this case, suppose the integer itself is 7928. Well, if we wanted to reverse it, for humans, it's fairly easy. We just write out the 8297 and it's reversed. But for computers to do it, there has to be a methodology for doing this. So the computer should follow the algorithm the computer can follow can be along the same lines that what humans do. So for example, first we pick out the first digit, 8, and then the next digit, 2, and then the 9, and then the 7, then it's done. So how is this done? Well, we can use two variables to track the progression, and in each iteration of the loop, we can reduce the problem size. So in the first iteration of the loop, we can keep our reverse number, we can set that to 0, whereas the input is the input integer x, 7928. So in the first iteration of the loop, we should pick out the 8 and store that in the reversed number 8. But at the same time, we need to reduce the problem size to ensure that when we run this loop n times, where n is the number of digits in this number, we're guaranteed to finish the problem. So once the 8 is taken care of, we should reduce the problem size by eliminating the 8 from the x. In the next iteration of the loop, we should move the 2 to the reversed number, and it should be incremented such that the 2 is added to the right side of this 8, while on the right side, the x, the problem size is again reduced. And this loop iterates until x becomes 0. When x is 0, this is an indication that our reverse function has completed its job and that we can return this value. So this is how conceptually this problem is solved. Let's look at the rough code on how this can be implemented. So this is not the complete code, but it captures the essence of how reverse is implemented. So first, we set reverse equal to 0. And in a loop, while x is not equal to 0, we should do a few things. First, we should pick out the least significant digit of the input x, and that's done by the remainder function. So this remainder function, when we call remainder 10, this picks out the least significant digit, which I call pop here. And then the x itself is reduced by removing the least significant digit. This is done by using the divide by 10 function. In addition to this, we need to check for overflow, but I'll explain this part a little bit later. So once we have the least significant digit, we need to think about how to combine the least significant digit and the remainder of the x to increment this loop. So that's done by this line. So the previous remainder is multiplied by 10. This is to ensure that there won't be any collision when we add in the new digit. So in the case as above, if you remember, in order to add the 2, the previous 8, we have to multiply by 10 to make it 80 so that we can add the 2. That's essentially what this line does, so that the reverse number is updated by the previous reversed number multiplied by 10 and adding the new digit. So essentially, this is how the reverse code is implemented. So what about this overflow check that I have left space for here? Well, to understand this, first we need to discuss what is an integer and how is it represented. So the way an integer is defined is it's a 32-bit representation. What this means is that the integer that for any given integer number, it's actually represented by a string of zeros and ones. And there's exactly 32 of them. So for example, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, dot, 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 dot. And then a string of 32 of them make up an integer. Because each digit, you only have a choice of either 0 or 1, the maximum integer that's represented by a 32-bit storage is 2 to the 31 minus 1. The most negative integer that you can get is negative 2 to the power of 31 without this minus 1. So if you do the math, the maximum integer that can be possibly represented is this number, while the minimum integer that you can represent with 32 bits is this number. It's different by 1. One might ask, why is the max different by 1 compared to the minimum? The reason is that it's not symmetric because you need to include 0. And 0, by definition, is stored with the maximum. So if this is a little bit confusing, here's an example to explain. If we only had 3 bits to represent a number, and if we use 2's complement so that we can represent both positive and negative number. So if we only have 3 bits, there are 8 possible numbers because 2 to the power of 3 is 8. So the numbers that are represented is minus 4, minus 3, minus 2, minus 1, and 0, 1, 2, 3. So here, as you can see, the most negative number is minus 4, while the most positive number is minus 3. And here's a bit representation for minus 4 to 3 using 3 bits. The same logic applies to the case for real integers, which are represented using 32 bits. Why is this important for this particular problem? It's because when the input is an integer, when you reverse it, it's possible that the reversed number is larger than the max number that can be represented using the integer format. So in which case, when we detect such a condition, we should return 0. So how do we know when the integer will exceed the max? Let's take a look at the code. So here's the complete code written in Java for the reverse function. The input is an integer. We set the reverse to 0, and we loop through the integer. We process 1 digit at a time, starting from the least significant digit, and we decrease the problem size by dividing by 10 each time. When this becomes 0, that means you have processed your entire input digit, and you can return the result. Now, in terms of the error check, the most critical line is this particular line where you're multiplying the previous result by 10 and adding the least significant digit. So this multiplied by 10, it's possible for you to go over your max integer storage space. So we added a check for that. So for example, if this previous reversed result is already greater than 1/10 of the max integer, when you multiply by 10, it will go over the int max number. This int max is the constant. This is equal to 2 to the power 31 minus 1, as explained on the previous slide. Or if the previous reverse number is equal to int max divided by 10, and the least significant bit is greater than 7, then you will also go over the max. Why is there a greater than 7, you ask? Well, it's because the int max I'll just write it here. Int max, it's equal to 2147483 647. So here's where the 7 becomes critical. If this previous reverse number is exactly equal to the int max divided by 10, but the least significant bit is less than or equal to 7, it's still okay because you can still represent that as an integer. But if it's greater than 7 and this is equal to 1/10 of the int max, then you will overflow. So the same logic applies to the negative case. So we check the positive case, we check the negative case, and then we apply the updated result in the while loop, and then we return the result. How does it work for negative numbers, you ask? Well, it turns out that the remainder function in Java or C++ also works for negative numbers. So, for example, if your input was negative 328 and you apply the remainder function of 10, the result would give you -8. So the code does not need to be changed, and you can directly run this code for positive or negative numbers, and the result should be correct. Try it for yourself. The end.